All right, so here are the examples for the section 9.1 and 9.2. So here's our first example. Z-test when sigma is known. Okay. So let's look at our example to the right there. Sunspots have been observed for many centuries. Let X be a random variable representing the average number of sunspots observed in a 4-week period. A random sample of 40 such periods from Spanish colonial times is obtained. The sample mean, X bar equals 47.0, and sigma is known to be sigma equals 35. Sunspot activity above those levels may indicate gradual climate change. Does the data indicate that the mean sunspot activity during this period was higher than the long-term mean of mu equals 41? Okay? So we can see here that the X bar is larger than mu, but is that significantly larger based on our data? Okay? So the first thing we want to do is get our hypotheses. That's part A, hypotheses. So we identify this problem is dealing with means. So our null and alternative hypothesis will have to deal with the population mean mu. Okay? Now, H naught is the alternative hypothesis. The alternative hypothesis says that there is no difference from the long-term mean here. So this would be equal to 41. The alternative hypothesis is going to test some claim. Is it bigger than 41, less than 41, or just not equal to 41? In this case, the problem indicates that we want to test to see if the data indicate that the mean sunspot activity during this period was higher than the long-term mean. So we want to test greater than 41. So again, you need to generate this symbol based off of the context of your problem, okay? Now let's go for our test statistic. Let's ask ourselves, is the central limit theorem satisfied here? Well, in order for the central limit theorem to be satisfied for the sampling distribution for a mean, we know that the random sample has to be bigger than 30 or the population's normal. In this case, our random sample is 40, so we are good to go with the central limit theorem. So let's get our z-test statistic. Remember, z was x bar minus mu naught over sigma x bar. Okay. So this is equal to, what's our x bar? 47 minus mu naught is 41 over our standard deviation for the sampling distribution, remember, is sigma over the square root of n. Make sure you use the right value there, not just sigma, okay? So let's calculate that, see what we get. I'm getting 1.08. So our z-test statistic is 1.08. Okay. Part C asks us to find the p-value. The p-value, or the probability value, comes from the area on the normal distribution. So let's draw that. This is our x bar distribution. Standard normal z distribution with 0 as our average. So 1.8 falls right here, let's say. 1.08 there. And we're testing the claim that mu is larger than 41. So we want the area to the right. So that's why it's important to have your hypotheses listed and correct, right? So that's just going to tell you that alternative hypothesis tells you which direction you're going to go. So let's get it. Our p-value will be equal to normal CDF, lower bound 1.08, upper bound 10 to the 99, 0 and 1 for our C distribution. So let's see what we get. Second distribution, normal CDF, throw in your values. So this is 0.1401, approximately. So part D is interpretation, right? Interpret results. This was test out, right? Okay. Interpret our results. So in this case, alpha is not given. So assuming alpha is the 0.05, remember that's the standard value that we normally use. Assuming that alpha is 0.05, what do we notice? How does the p-value compare to this? Well, the p-value is larger, right? P is greater than alpha. So that means that there is a high probability that we produce samples under this distribution, the null distribution, when this guy is true, right? So what that gives us is, P is greater than alpha. We retain the null hypothesis, right? There is not significant evidence to support that the average number of sunspots from this period was higher than 41. All right, so you can go back to the PowerPoint. We'll deal with the situation where sigma is unknown next. All right, so let's take a look at this next example. Here, example. Hypothesis test for mu when sigma is unknown. So again, hypothesis test for the population average when sigma is unknown, okay? All right, so here, first things first, we want to figure out our hypotheses, right? So A, hypotheses. So the null and alternative, we're dealing with means here. We will perform hypothesis tests that don't involve means, actually involve proportions, next class, okay? All right, so let's think about our null hypothesis. Null hypothesis is always equal, doesn't matter, because that would be that the mean is no different than the actual population mean. In this case, mu is, well, what is mu? So if we look here at our example, we know x bar is 2.92, but that's not mu. S is 0.85. It comes from here. Does the data indicate that the mean length is longer than 2.6? So from our question stem, it said that the average length of all the arrowheads was 2.6. Alternative hypothesis also comes from that statement. Does the data indicate that the mean length is longer than? So we want to test to see if it's bigger than 2.6. So you can see here that the average, the x bar, the sample mean is bigger than 2.6, but is it significantly bigger? Is there evidence to support the claim that from just this one sample that we have larger arrowheads? Okay. So B, our test statistic. We have to calculate that. So here, remember, we're doing a t-test. We have to do a t-test because sigma is unknown. So our test statistic t is equal to x bar minus mu over s over the square root of n. Okay. So let's plug in those values. 2.92 minus mu is 2.6 over s, which is 0.85, divided by the square root of our sample size. So our sample size was 61. 61. So let's see what we get. So here I'm getting 2.91. Okay. 2.91. All right. Now that we have our test statistic, we can find that area. So here we're finding our p-value, which is the area on the t-distribution corresponding to the right of our 2.91. So let's draw our t-distribution. T. Mean is 0. 2.91 over here. And we're looking for that area to the right. Again, we're looking for the area to the right because of our alternative hypothesis is greater than that value. Okay. So this time we're trying to find a probability on the t distribution. So p is going to be equal to t CDF. So here, let's go there. So second distribution, if you go down to option number 6 is t CDF. So here we have to put in some values. Our lower limit, which is 2.91 in our case. Our upper limit, which is 10 to the 99. And then we need the, if you look there, degrees of freedom, which are 60, n minus 1, right? So let's plug those in. 2.91, 10 to the 99, and 60. 0.0025. Okay. Part D deals with our interpretation of our results, right? So the conclusion. So here, did we specify an alpha level? It doesn't look like it, so let's just use 0.05. So assuming alpha equals 0.05, how does our p-value compare to alpha? Well, it's smaller this time, right? P is less than alpha. So let's think about what that means. That means that it is unlikely, because it's so small, it is unlikely that we would obtain a sample of like the one we got, a sample mean, 2.92. It would be very, very unlikely to obtain a sample mean if the null hypothesis were true. So if this were true, it would be very unlikely to get a sample like we did. But in fact, we did get this sample, right? We did get this sample. Therefore, there is evidence against the null hypothesis. So we reject H naught. There is significant evidence to support the claim that the average arrowhead length at this site is longer than 2.67 years. All right, you can go ahead and go back to the PowerPoint now. All right, so let's look at this example now. So example 3. All right, so in Wilmington, North Carolina, the annual amount of snowfall is normally distributed, and the annual average snowfall is known to be 1.4 inches. A researcher believes that the mean snowfall has changed. So the researchers take a random sample of 16 days, and the sample mean of 1.1 inches, and a sample standard deviation of 0.27 inches is recorded. Test the researcher's claim at alpha equals 0.05. All right, so we know we want to test the researcher's claim. That means we're doing a hypothesis test, right? So we got to think about which hypothesis test is appropriate. Are we going to do a z-test here or a t-test? Well, we do a z-test when sigma is known, when the population standard deviation is known. Do we know the population standard deviation? No, we don't. We don't have any information about sigma. So we know that sigma is unknown here. Unknown. We use t-test. Use a t-test. All right, so now we can get started. So our A is our hypothesis, hypotheses, H naught. All right, we are doing a hypothesis test for the average snowfall. So we're testing for a population mean. Our null hypothesis is always equal, so what is the population mean here? So we go back, the annual amount of snowfall is normally distributed. That's good to know. And the annual average snowfall is 1.4. So this is telling us mu, right? The sample mean is 1.1, so that's x bar. So make sure you note the difference if it's not spelled out for you. So here, the overall average is 1.4. All right, what claim do we want to test? Well, the researcher believes that the mean snowfall has changed. So it doesn't tell us a particular direction to go, neither greater than or less than. So let's do the not equal to here. He thinks it has changed from 1.4. Okay. Note that these values are always the same number. Okay, talking about mu. Test statistic. So here we have to pick the right formula. Remember, we're doing a t-test, so we're going to find a t-test statistic. X bar minus mu over S over the square root of n. So let's plug those values in. What is our test statistic? Sample mean is 1.1. Mu is 1.4. Over S, our sample standard deviation, is 0.27. Over the square root of n, which is 16. Okay. So calculating that, we get negative 4.44. Okay. It's a pretty big value, right? If we're more than 2 standard deviations away from the mean, we usually get a small probability. So see our p-value. Let's draw it. So t, 0 there. All right, so negative 4.44 is all the way over here. Now recall that this one's a little different, right? Because since we're testing for a difference, just a difference, we have to test, yes, to the left of negative 4.44, but also to the right of positive 0.44. So there's two-tailed. This is a two-tailed test. Two-tailed test. So we want both of these areas, here and here. Okay? But recall that both of these areas are exactly the same, right? These areas are the same value. So all we need to do is find one of them and then multiply it by 2. So our p-value is equal to 2 times t-CDF of something, right? So again, it doesn't matter which one you find. So let's do this red area. So our lower bound would be negative 10 to the 99. Upper bound's negative 4.44. And then t-CDF requires the degrees of freedom, which would be 15 here. Okay? So that's how we're going to input it into our calculator. 2 times, do 2 times first, and then access distribution. Distribution t-CDF, and then let's put in our numbers. Negative 10 to the 99, negative 4.44, 15 degrees of freedom, paste it in. So we're getting 4.77, yada, 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 and watch out for that little e to the negative 4, which means we were going to move this decimal 4 places to the left. So this would be 0.0005. So again, if we move this 3 places to the left, or it should be 4 places to the left, we have 3 zeros and then 4 sevens. So that 7 will round the 4 to a 5. Okay? So you have our p-value. It's very small, right? It's very small, which means that there's evidence to support our claim here. Okay? So our conclusion. We know alpha this time. With alpha equal to 0.05, p is less than alpha, we reject the null hypothesis. There is significant evidence to support the claim that, and again, always spin it back in terms of your situation. So here we're dealing with average snowfall, right? So there's significant evidence to support the claim that the average snowfall differs from 1.4. Differs from 1.4 inches. All right, I think the next 2 examples deal with so we have another one here. So let's do this one. Okay. All All right, so CNN Money reports that the mean cost of a speeding ticket, including court fees, was $150 in 2002. The local police department claims that this amount has increased. To test their claim, they collect data from a simple random sample of 160 drivers who have been fined for speeding in the last year, and find that they paid a mean of $154 per ticket. Assuming that the population standard deviation is $17.54, is there significant evidence to support the police department's claim at the 0.01 significance level? So alpha's changed, correct? All right, so let's think about it. Is this a z-test or a t-test first? First things first. Z-test or t-test? So in here, do we know sigma? Do we know the population standard deviation? We do. We know the population standard deviation is 17.54. So sigma is known this time. We're going to do a z-test instead. Okay? Z-test instead. So A, hypotheses. Okay. So we're testing means here. It's always equal for H naught, right? So what is the mean here? Here the mean is 150, right? So we're trying to test to see if this average has changed or has increased since 2002. So our mean is 150. Population. What claim are we trying to test? So the police department claims that this amount has increased, so that the mean has gone up more than 150. Okay. Test statistic is a z-test statistic this time. So that's x bar minus mu over sigma over the square root n. So what's our x bar? So here we have collected data from a simple random sample of 160 drivers. Okay, so that's good because the sample size is bigger than 30. The mean was 154 minus our null mean over sigma 17.54 over the square root of 160. So let's see what we get. Getting 2.88. Next up is p-value, right? We need to find the probability of getting a sample like we did under this distribution. So C is our p-value. Draw our picture. This is Z. Okay. And 2.88 is our Z value, so that's up here somewhere. Now, do we need the other tail? Well, no, because it's just greater than, so we're just looking one direction. This is a one-tail test. We need that area there. So our p-value is normal CDF. Lower bounds 2.88 to 10 to the 99, 0, 1. Okay, so let's see. I'm getting 0.0020. That 8 rounds to 9 and the 9 rounds to 1. 0020. So conclusion. With alpha equal to 0.01, P is smaller than alpha. So what do? We reject the null. Again, why do we reject it? It's because there is a very, very low probability of getting a sample like we did if this were true. So this must not be true. There is significant evidence to support the claim that the average speeding ticket costs more than $150. Okay. So let's go back. Our next example. All right, so here we're dealing with, so here we can actually use the calculator to do this entire process for us, okay? So let's look. All right, so here are the steps to do a particular test, okay? So there's a lot of different options for different types of tests, so we'll figure out which one to use and how to do it, okay? So let's look. Studies conducted in 1970s indicated that the average age at which children take their first alcoholic drink is 14.6 years old. Sociologists believe that children are starting to drink at a younger age. A simple random sample of 144 young adults is selected, and the age at which each adult took their first alcoholic drink is recorded. The sample mean age was 13.3 years of age. The population standard deviation is known to be 5 years. Test the sociologists claim at the 0.01 level. All right, so first things first, we need to figure out what our what type of test we're going to use. Are we doing a z-test for the mean or a t-test for the mean? Using your ti to do a hypothesis test. All right, so is this a z-test or t-test? Well, we got to know the population standard deviation. The population standard deviation is known to be 5 years. So sigma is known. Do a z-test. Okay. All right, so here's how we do it. So we're going to go to second distribution. Excuse me. Second stat. Excuse me. Stat. Go to stat. Go over to tests. So go over, and you can see a bunch of significance tests here, okay? Let me see if I can. Manipulate this a little bit. Right, just trying to get so that you can see this. So here we have a bunch of tests. So we hit stat, we go to tests. So you can see here we have a z-test, a t-test, 2 sample z-test, 2 sample t-test, 1 prop z-test, 2 prop z-test, so on and so forth. So here for this section, we're only going to be dealing with z and t, okay, for these 2 sections. So what was it? We had a z-test. So hit z-test. Now it's going to ask you, do I want to do the z-test from a list of data points or from given statistics? So here, we're not dealing with any data, like our arrowhead example. So we are given all the statistics. So go ahead and hit stats and hit enter. And then you should see all of your values that you can plug in here, okay? All right, so what is mu naught? What is our null mean here, okay? Null mean would be the average from the 1970s, which was 14.6. What is sigma? That's the population standard deviation, is 5. X bar is our sample mean, which was 13.3. And n is our sample size, which is 144. Okay? What do we want to test? We want to test the claim that the sociologist made, which means that they believe that children started drinking at a younger age, which means that the null mean is less. So our mean is less. So we're going to choose less than option. And we'll go to calculate. Hit enter. Enter again. Excuse me. Let's go back. Stat, calc, to tests, z-test, calculate, and here is our z-test, okay? So it's telling us our alternative hypothesis, mu is less than 14.6. The z-test statistic was negative 3.12. Our p-value is, so let's write that. So mu was less than 14.6. Our test statistic was negative 3.12. P was 0.0009, and n was 144. Okay? So based off this p-value, we can conclude with alpha equal to 0.01, p is less than alpha, we reject the null hypothesis. There is significant evidence to support the claim that the average age of children taking their first drink is below 14.6 years old. Okay. All right, and I think that we'll stop there. So you have a bunch of examples to deal with. Here, we would have to input all that data into the TI, so I won't be doing the last example. All right, so you can go ahead and get started with WebAssign. There's problems there.